Okay, this is my demo 8. I'm going to be demoing on 9A, 9B, 9C, and 9D. For 9A, it's I can draw state diagrams to represent FSMs. So I'm going to draw a state diagram to represent a more FSM using this transition table right here. So looking at it, we have A, B, and C, so that we have three different states. I'm going to go ahead and put 0, 0 for A, 0, 1 for B, 1, 0 for C. And so looking at it, each state has two different options it can go. It can either, so for A, it will go to back to A when the input is 0. So we'll take an arrow and we'll draw one back into A, and that's when the input is 0. And then it can also go to B when the input is 1. So we'll draw an arrow to B. That's when the input is 1. So now we're in state B. B also has two options. It could go to back to A when the input is 1. So we'll draw an arrow back to A when the input is 1. And it can go to C when the input is 0. So we'll take an arrow, we'll draw it there. And that's when the input is 0. Okay, so now we're in state C. C will go back to B when the input is 0. So we'll draw an arrow back to B. Back to B. And that's when the input is 0. And then it will move to A when the input is 1. So we'll take an arrow and we'll draw it to A. And that's when the input is 1. And so that's pretty much how you draw a state diagram and kind of the flow of it. I'll move on to 9B now. 9B is I can complete next state tables to summarize FSM operations. So I'll go ahead and just go kind of row for row. Looking at the state diagram, we know that each present state has two paths it could take. So if we fill, that's why I already have this filled in. So we have AA, BB, CC because of that. So then we'll just start with, here, it'll be easier if I do this. So A can either go or stay at A. So we'll put in an A here. And so the Q1 and Q0 of those are both 0. So we'll fill in that. And then our D inputs will also be 0, 0. Then A also can go to B, so we'll put in a B here. As we can see right here, A can go to B right here when the input is 1. So A is 0, 0, and then B will be 0, 1. And then that'll make our D1, 0, and our D0, 1. So now we're in state B, and we can either go to C or back to A. So B, we'll go C right here because we can go to state C, or we could go back, or let's do A first. We'll go to A, or we could go to C. So if we're in B, the Q1 and Q0 is 0, 1. Oh. And then if we're in A, back to A, it'll be 0, 0. So that'll make our D1, 0, and our D0, 0. And then if we were to go to C, 0, 1 for B, that will put us at 1, 0, now that we're in state C. And that'll make our D1, 1, and our D0, 0. Looking at, so we went from B, now we're in C. C also has two paths. It can go to A or it can go to B. So C, it can either go to A or it can go to B. And then it's just a matter of filling in the Q1 and Q0 for each one. So C is 1, 0. So we'll fill in that, 1, 0, and then A is back to 0, 0, so that will make this D1 and D0, oh, that's a, oh, that'll make this, oh my gosh, 0, 0, I think I put O's for those on accident. And then if we were in B, that'll put us back to 0, 1. That'll make our D1, 0, and our D0, 1. 0, 1. Okay, yep, that looks right. So that's how you take your state diagram and you fill out your next state tables. And so for 9C, I can implement FSMs with logic circuits. So I'm going to take this state diagram and then this next table, and I'm pretty much going to use that to demonstrate C. So from here, we can now fill out our K-maps. And so when we do, we don't count 1, 1, so that's why there's X's there. And we only get a 1 right here. So that means D1 is equal to not Q1 and Q0 and not the input. I stands for the input. So that's our first Boolean equation for D1, our D1 flip-flop right here. And then our D0 flip-flop, same thing, we don't count 1, 1, and we get a 1 at 1, 0, 0, and 0, 0, 1. And so that'll give us for, let's see, this one is this one. So it's not Q1 and not Q0 and I, or Q1, so now we're in this one, Q1, not Q0, because we have 1, so not Q0, and not I, because we have 0. So those are our two Boolean equations. So now I'm going to go into Logisim and show you this circuit. So the way I designed the circuit is we're going to obviously need 2 D flip-flops for our Q1 and Q0 right here. So we have 2 D flip-flops. Then we have our input pin and a clock. So there we go. And so so we need to create our inverters, so our NOT gates. So we're gonna grab 3 NOT gates. So we have one right here, and right here. And so one is for the NOT Q1. So here we have one for the NOT Q1, and then one for the NOT Q0. So here we have one for the NOT Q0, and then one for the NOT input. And these are coming straight from the equations that we just derived. So NOT Q1, NOT Q0, and NOT input. And so for so there, and then we'll need an AND gate with 3 inputs. And so that is for the NOT Q1 and Q0 and NOT I. So we use that one for that equation. And then we do the same thing for the Q0, which is NOT Q1 and NOT Q0 and the input. So here we have the input and then NOT Q0 and NOT Q1. And so that's how those are for the logic for the D1 and D0 flip-flop. Okay, and then we have this third AND gate with 3 input pins. That's for the Q1, which is the output of the first flip-flop, the NOT Q0, and the NOT input. And so this is going to be our term 2. And this one right here, our term 1, this is for the NOT Q1, NOT Q0, and the input. And we combine both of those to give us with an OR gate. That's from our second equation. Here, I'll go back and show real quick. This is for our second equation, this one right here. So this is the OR gate right here. So we have our not Q1 and not Q0 and I, or then our Q1 and not Q0 and not I. So that's what, let's go back to this. So that's what this OR gate is for. And so yeah, so let's test it now. So right now we should be in state 0, or state A, which is 0, 0. So we'll clock it. We're in state 0. And then if the input is 1, we should go to B, which is 0, 1. So we'll change the input. We'll clock it. Now we're in B, 0, 1. Okay. And then if we change the input, if we keep it at 1 and clock it, we should go back to A. So we're back to A, 0, 0. So then I'll put us back to B. And if we change it to 0, we should go to state C, which is 1, 0. So we'll turn that off. Now we should go to 1, 0 once I clock it. And we do. From state C, we'll go back to B when it's 0. So if I clock it again, we go back to B, 0, 1. And then I'll put us back to C. And if it's 1, the input, we should go to A, which is 0, 0. Clock it, and boom, it's working. So that is how I designed the circuit, and it shows that the circuit works. So now, go out of here. Okay. So now we'll move on to 9D. So 9D is I can design FSM counters. So I'll be designing a 2-bit synchronous up counter. And so here's the state diagram. Since it is a 2-bit synchronous up counter, there is no input. It's just every clock pulse will move to the next state. So we'll go from 0, 0 to 0, 1 to 1, 0 to 1, 1, and then we should loop back to 0, 0. And so same thing, we'll based off of that, we'll build our next state table. So A can only go to B. So here we see A going to B. So then we're in present B now. B can only go to C. So we have C here. And then we're in C present. C can only go to D right here. So then we're in D present. And D can only go to A. And we're in A present. And then Q1, Q0, they're all right here. Q1, Q0. And then the D1, D0 follows this one. So there we go. That's our next state table. So then we'll take that and we'll do the same thing. We'll make a K-map for D1, D0. So for D0, at 0, 0 and 1, 0, we have a 1. And so that gives us the Boolean equation of not Q0, because they're both 0, not Q0, Q0, so that's, yep, okay. And then for D1, we end up with hold on one second. Yeah. So for D1, we end up with Q1, X or Q0. And so now I'll show this circuit in Logisim. Sorry, let me pulling up my notes. Okay, so I'll just kind of, since that was pretty brief on the equation, I'll kind of just explain why I designed the circuit this way. So obviously we start with 2D flip-flops because we have a Q1 and Q0. Why though is because we need 2 bits to represent the 4 unique states, which is 0, 0, 0, 1, 1, 0, or 1, 1. Each D flip-flop stores 1 bit, so we use 2. And then, so Q1 is the most significant bit, and Q0 is the least. So then from there, so I added the 2 flip-flops, then from there I added a clock. This is a synchronous FSM, so it updates its state only on clock edges, usually rising edge, and we connect the same clock to both flip-flops so they change the state at the same time. So that's what makes it synchronous. So obviously it's hooked up to both at the same time. So that's what makes it synchronous. And then from there, I connected Q1 and Q0 outputs to the logic gates. So for Q1 output, I wired to one input of the XOR gate, and then also wired to a output here. And then for the Q0, I wired to the second input of the XOR gate for the Q1 XOR Q0 equation that we got. And then I also wired to a NOT gate to compute for the NOT Q0. And then from there, I wired to our second input, which represents our Q0. So why I did this is we use Q1 and Q0 to compute the next values, D1 and D0, using logic gates. So Q1 XOR Q0 determines the next value for Q1, and then NOT Q0 determines the next value for Q0. And then from there, I connected logic gate outputs to the D inputs. So the output of the XOR gate is the D input of the Q1 flip-flop, and this implements the D1 equals Q1 XOR Q0. And then the output of the NOT gate, which is the D input of the Q0 flip-flop, this implements the equation D0 equals NOT Q0. And why I did this is because these D inputs control what value will be loaded into the flip-flop on the next clock tick. Based on the current state, Q1 and Q0, we want to set the next state by sending correct values to D1 and D0. And so that's kind of my explanation for it, and I'm way over time. So I'm going to go ahead and test it real quick. So for some reason, it doesn't let me do it like that. Okay, so I should have reset it. So, okay, here we go. We're in 0, 0. So then we should go, every clock pulse, we should switch a state. So we're in 0, 0, state A. Now we're in 0, 1, state B. Now we're in 1, 0, state C. And then 1, 1, state D. And now once I click this, we should loop back to state A, which is 0, 0. And we do. So the circuit is working, and that is my demo 8.